Okay, so there's a few conventions that are different, but the big question is, why would you use alternating current versus direct current? Go ahead.
Different power sources or frequencies.
They come with a different frequency. Direct current has a frequency of 0, right? It doesn't change at all.
Alternating current is easier to travel long distances.
That's it. It's easier to travel long distances. What are some disadvantages for alternating current?
Most of our devices use direct current.
They do. They do. You have to convert it once it's in the house, typically, to DC. Because DC, so why don't we generate in DC? AC is also, DC is less physically detrimental to us if we get involved, if we connect ourselves with electricity. DC doesn't hurt us nearly as bad. So that's the disadvantage. The big advantage, though, is being able to travel distances. I don't know if you guys ever watched any videos where Edison was arguing for DC current. He really thought DC was the way to go. Health perspective was the main one. He at one point he demonstrated it by killing an elephant with AC current on the stage. I think that was detrimental to his whole reputation when he did that, but it was his choice. DC, when we travel long distance, voltage equals current times resistance, and those cables that run all over the place carrying our electricity around, they have a certain amount of resistance. And for the voltage that and remember, our power losses are I squared R. So the higher your voltage went, your resistance didn't change, does it? I mean, you build those lines, your resistance isn't going to change. So as the voltage goes up, your current goes up, and therefore your losses go up tremendously through the power losses in the line. And when we deal with alternating current, we can up the voltage significantly, and we don't have all those losses that DC produces. There was a study once done, it was in the 70s, so I'm sure it would have to be more now, that if we were to produce enough electricity using DC to power our society, we would have to have a square mile plant every 10 miles. So it would be a huge amount of land space to produce that.
Well, that was one of the big arguments when Edison was advocating for DC power grids in cities like New York. Because the issue that they realized is it would be, every 2 city blocks you'd have to have a jump up station.
Yep. And so it wasn't a good alternative. So we went to AC. And AC, what it really is, I got a website here. It has to do with the generation of AC. And I used to have a nice moving picture, but I couldn't find it. I don't know where it went. AC is simply, there's a magnetic field that's produced around any magnet. You guys have seen these, haven't you? Have you studied those yet at all? The EMF, there's a magnetic pole between north and south pole. And there's always what are called magnetic flux lines that travel between the two. You guys ever sprinkled iron core in a magnet and saw it go around it? They're invisible to the eye, but they're there. There's a lot of study around them. And when you put a wire through any of these magnetic fields, it produces a current. And therefore, if you have a current and you have resistance, you have voltage, right? And I brought a few here that are just simple generators. And basically what it is you have this wire that goes through, and as it rotates through this field 360 degrees, it's going to produce, when you're level with it, it's not going to produce anything when you're in line with those flux lines. But as soon as you start breaking that and moving up, it starts creating current until it is perpendicular with those magnetic lines. And then it's at a maximum value. And then as it turns, so it turns 90 degrees, and as it goes through that, the current increases and increases from 0 It's going to go up like this until it hits 90 degrees. And then you're going to start bringing it back until it comes back to 0. That current is then at 0 again. And then on the other half, it's going to start creating the current, but the current's going to go the opposite direction because you're actually just rotating the whole thing until you're again perpendicular. And then it's going to go back up to 0 till it's at the starting position. So then we have a sinusoidal wave. And you can do this with a lot of simple things. It doesn't take a lot to be able to create AC voltage. And I got a few little things here. You guys probably did these in elementary school, where there's just a magnet inside this. And when you rotate that, this is the one that needs work, rotate that magnet, and you don't have to rotate it too much, you generate electricity. So it all has to do with that magnetic field that's produced here. This is just a really simple little generator that turns. Get enough going, you can turn anything. Okay? If you go backwards, the current's just moving the other direction. That's the only difference that it has, is which direction you're turning that. So that's how we end up getting an AC waveform. Is simply turning. You either turn the wire inside that magnetic field, or you turn the magnet. Okay, you can do it either way, and you'll see generations made either way. I think more often than not, they'll be turning the wires inside the conductor inside in order to produce that loop. Going through the whole 100. Yeah, I don't think there's anything else in here. Here's the wheel that shows it. As it turns through the wheel, as it turns through, depending on where it's at, remember we saw our theta, it's going to come through and create the sinusoidal waveform for the whole 360-degree circle. Okay, I am going to use, here's another picture that shows it pretty good. You can see the flux lines, and as it turns through, it's going to create a voltage. I'm going to use some slides from the book just because they're really good for this chapter. And I like the pictures, and I'm not real good at drawing these pictures, so this is what we're going to use these directly from the book. I guess I could do this. And I didn't really gleam anything out of here. So we're going to learn to graph a sine wave and a cosine maybe. We're going to find instantaneous values, the peak and RMS values of voltage and current, period and frequency, and we're going to determine the phase angles. So that's what we're going to talk about this week. It's produced by a coil of wire rotating in a magnetic field. That's the whole gist of it right there. It's a coil of wire rotating in a magnetic field. So it's the mathematics of the sine curve is what we're looking at. The basic sine curve can be created using angles in degrees and radians. So I graphed this, and I was going to show you guys what it looked like. Let's see if I can bring it up. Here it is. This is just an Excel spreadsheet graphing just a sinusoidal function, and I carried it out to 360 degrees. I think that's what I have. 360, yeah, I went to 360 degrees. And so it always looks like this. This is the standard sine wave that we're going to look at. You'll look at for the rest of your career. And get really close with it. So they went through this and did it. There's the sine wave. I want to get to this one picture. Here it is. The sine curve always begins at 0. If you put sine 0 in your calculator, you're going to come up with 0. If you put sine 360, you're going to come back to 0. Okay, when you make that complete loop, it goes from 0 to 0. Our maximum is at 90 degrees. Maximum is at 90 degrees. So this is the first quadrant, 90 degrees. When we get to looking at sine functions with current and voltage, you need to be in radians. Most of the time you're going to be in radians. Now I'm going to go back and forth because you guys are used to degrees, right? That's what your mind thinks of. You don't look at, say, pi over 2 and know exactly what that means. You're going to put it in degrees. So we return to 0 at 180 degrees, and then it reaches a negative peak at 270 degrees. I think there's a good picture in here that puts it. Okay. The amplitude. Okay, a new word. The amplitude of a sine wave. So I'm going to write this down here. So this is our sine wave we're going to use. This is our sine wave. And we're going to say y equals x times sine of theta, whatever theta is. They use A. I'm going to use A like the book does. Y equals A sine theta. A sine theta. The absolute value of that A, no matter if it's positive or negative, it doesn't matter, you're looking at the distance, is called the amplitude, okay, or the peak value. It's going to give you this number right here. This is the amplitude. Peak value. So if we're talking voltage, we're usually going to use V with a subscript of peak. This is our peak voltage. I'm going to write it up here. Voltage peak equals peak voltage. When you guys do a lot of reading and calculating for these sine waves, it's real important that you indicate which one you're talking about as we go through this. So that's our peak voltage. Should have got rid of some of these. There's a good picture in here I want to get to. Maybe. Let's see if I can find it. Oh, come on. It's not even in here. I thought I stole it from them. I'm going to go in and find this, just the picture that I want. Sorry. This is it. Okay. This is the picture that I thought was in there, and that was the reason I was using it. So far we've studied the circle, right? Where everybody's good with the circle. When we found R and we found our theta, let's write these down real quick. We had tangent, theta, what'd we say? R squared, x squared plus y squared equals theta. What else did we do with that circle? X squared plus y squared. We found the magnitude of anything. Do you guys remember how to find the magnitude? Pythagorean's theorem. So we could find our theta, and we could find our R value. And if you look at this like you rolled out the circle across your sine wave, at 45 degrees, theta at 45 degrees, this is your R value at that point, and then carry it on your Y value, whatever the Y value was at that point. Whenever X is at 0, Y is at a maximum. Going through here, the amplitude in this one equals 1. Angular period, okay? Angular period is how many degrees does it take to go through one complete sine wave? And what would that be? This is the angular period. Have to be careful because we use that word for another one too. Angular period, if this is 180 degrees, or pi, this is 0 degrees, 0 pi. This is 360 degrees, 2 pi. To make one full angular period. Typically when you're looking at these, that's what you're going to look at. One full period of this. 360 degrees are 2 pi. That's your angular period. So basically, if you think about this thing, the value of y as you roll it out, if you rolled out the circle, this is what it's going to look like. Let me see. Well, let me look at the next one. Let's see what the next one is. Oh yeah, when we move it, we're going to come back to this. I'm going to go back to my spreadsheet here. So I have my sine wave. I have an amplitude of 1. So when I wrote, do you guys know Excel at all? A little bit, maybe? I think I'm going to roll it into some other parts. But what I did here, just to show you what I did, in this column right here, where that's what it's graphing, I took the amplitude times sine times or theta. Okay? So if I change the amplitude, this is the amplitude right here. So currently what I wrote is y equals 1 sine theta. And theta went from 0 to 360 degrees. If I change this to say 2, my sine wave now has an amplitude of 2. Okay, all I'm doing is increasing the top and decreasing the bottom of the sine wave. So we have the positive amplitude and the negative amplitude. And they're always going to be the same. So if I change this to say, I don't know, let's go 18. Now just the amplitude of this changed. Now it's at 18 for both the positive and negative. Notice the shape did not change. The shape did not change for this. It still is a sinusoidal wave. It's about the same. Oh, I need to change this. Okay. So we have our angular period, the amplitude, and when we write the sine function, this can represent voltage or current. They both follow the same path. So we use a lowercase v for instantaneous voltage in AC. Lowercase v. So typically, you know you're in AC when you see lowercase values. We always used uppercase for DC, right? So this is going to be our voltage peak. Instead of A, we just write it because that's our amplitude. It equals the voltage peak equals times sine theta. My theta, not cursive. Whatever theta happens to be. For current, we use the lowercase I, the peak value times sine of theta. Whatever theta is between 0 and 360 degrees. Now, remember I told you we spent most of our time in quadrant 1 and quadrant 2? That's where we spend most of quadrant 1 and quadrant 4. That's where we spend most of our time, right? If we look at this, there's quadrant 1. As we roll out the circle, I'm going to bring up my notes. I like that picture better. So there's the picture of the circle and it rolled out. The angular period, it's not T, it's, I have to correct that. Angular period shows our amplitude. Did I do quadrants on this one? I don't know if I did or not. Okay, angular period. Let's look at this and see what we come up with. We're going to go ahead and graph one of these. If you change the amplitude, let's just go ahead and do this on the board. So put these. And we're going to say this is 0. And we're going to do voltage equals our peak voltage. Let's not make it the same as that one. Let's make it 3 sine theta. So let's do some values with theta. V and theta, 0, 45, 90, 135, 180, we'll go to 270, and I'm going to put on 45, 310, and 360. So if I look at this and say this is 180 degrees, this is 360, 1, 2, 3, 4. Okay, what is my instantaneous voltage? The little v equals instantaneous voltage, and that means what is it worth? What is it at that specific point in time? So at theta equals 0, what's my value for my voltage, my instantaneous voltage? You guys got calculators? What is it at 0? 0. What is it at 45 degrees?
2.12.
2.12. 2.12, it's about right here. At 90? What is it at 90?
3.
135?
Uh, 2.21.
2.21, and then at 180, we come back to 0, right? What is it at 225?
Negative 2.12.
270, we're going to be at 3. And negative 2.1 here. And we connect the dots. And hopefully it looks something like a sine wave. 360 degrees. That takes us through the whole spectrum. Okay, remember 0 to 90. This was quadrant 1. This was quadrant 2 in our circle, right? Quadrant 3 and quadrant 4. If we were going to roll out the circle, that's how our quadrants would work out. And this is V equals 3 sine theta, whatever theta is at the value. What's our amplitude or our peak value for this? Yeah, it's given to you. You don't have to do a lot of work for this. Usually the volts is written right at the end. Okay, it's 3. Okay, some other vocabulary we're going to have here. I'm going to put all these in the same place. I think I'm going to turn this off for now and we'll put them there. Okay, V equals VP sine theta, and instantaneous voltage for current equals current peak times sine theta. Voltage peak equals the amplitude, and it's given to you, current peak equals the amplitude. And those are really used, and you can use them either way. You'll hear some people use amplitude all the time, and some people use peak value all the time. It means exactly the same thing. There's another value that's very, very common. You'll see it on all of the DMMs you look at. It's called peak to peak. So voltage peak to peak, this is called peak to peak value. And what that means, it's the distance between your upper value and your lower value. Okay? So it's twice VP. Voltage peak to peak equals 2 times voltage peak. You don't literally add them, you just add the absolute value of them. 2 peak to peak. Current peak to peak equals 2 times current peak. Okay, 2 times current peak. Now, that's the instantaneous value of anything. We can find the instantaneous value for anything. Let's find the instantaneous value here for this one that we have. We want to know what V equals, what's the instantaneous voltage when we're at, 57 degrees. When theta equals 57 degrees. What's our voltage peak going to be there? How would I find it? We're just going to write down our formula. 3 times sine 57 degrees. 2.51 volts. We can look at our graph. 2.51. Yeah, that's probably where we're going to be, somewhere in there. Let's say you have this current equation. I equals 15 times sine theta milliamps. What's my instantaneous current when theta equals 84 degrees? So you're going to put in your calculator, I equals 15 times sine 84 degrees. .92. Does that make sense? If you look at the rule of thumb, let's think of a rule of thumb for this, milliamps. Always go back and take a look at your graph. If you're close to 90, you're going to be close to the peak value. If you're way far away from 90, you're going to be pretty far away from what the peak value is for this. So what's our peak to peak value for this one? What's our peak to peak value? 6 volts, just 2 times. What's our peak to peak value for this one? 30 milliamps. Okay, peak to peak. Okay, well, we don't usually talk about the peak to peak unless you're doing a lot of measurement and design. That's when you're going to use a lot of the peak to peak values. We use what's called RMS. If we took the average of a sine wave, just the average, you have the equal amount negative as you have positive, right? When you look at this area right here is exactly the same as this area, isn't it? So what's the average? What's the average of 10 and negative 10? 0. Negative 4 and 4, it's 0. So we don't use the average. We use what's called the root mean square. And the root mean square gives us what the actual value, if we were to completely change this to a DC current, if we were to take this alternating current and power something to get that same amount of power out of this as you would if it was DC, that's called the root mean square. Root mean square. RMS value. And that's what you always hear called as the root mean square. And so the root mean square, and it's RMS, and you have to use the subscript. So everybody knows you're not talking about peak or peak-to-peak value. Root mean square is 1 over the square root of 2 times our voltage peak. Can somebody put in their calculator 1 over the square root of 2?
0.707.
0.707. 1 actually. That number comes up a lot in electronics. You'll see it quite a bit. 0.7071, 70%, 70.7%. You'll see that number come up a lot. So voltage root mean square equals 0.707 times our voltage peak. And this gives you, this RMS value of the voltage gives you the same power that you would get if it was a DC circuit, if it was a direct current circuit. And it's always, so if this is 1 volt, our root mean square is going to be 0.707 volts. And it's going to be a little above half, 70% of what that peak value is. So this is our volts RMS. Volts peak is up there. Volts RMS. Always a positive value. So I'm going to put these. Same thing for current. Volts RMS equals 1 over the square root of 2 times voltage peak. And I don't care which one of these you use either one of them. I RMS equals 1 over the square root of 2 times I peak, 0.7071 times I peak. Use either one of them. Root mean square. The value of a DC value that produces the same electrical energy as the AC voltage or current. Let's do one. We have a value of, let's say we say voltage peak equals 170 times sine theta. Whoops, this is little v. V. Let's write these out so we can figure out what's our voltage peak. What is it? 170, given. Given. The voltage peak is always given to you. If we, let's see if we can just kind of sketch this graph out. 0, we're just looking at one angular period. One angular period. 0 to 360 degrees. Does that sort of look like it? 0 degrees, 360 degrees. Whoops, our 2 pi. I'm going to get a little closer to that. Peak. $170 volts. What's my voltage going to be here? 0. 0. What's it going to be here? 170. Negative 170 degree volts. Okay, what's my peak to peak value?
340.
340. This is just 2 times voltage peak. Voltage RMS. 1 over the square root of 2 times 170.
$120.2.
120 volts. 120 volts. If you don't have a subscript on this, if I just say volts equal, assume RMS. Okay, if it's not given, assume RMS. Okay, the peak to peak voltage coming out of this wall is between 160 and 170. Everybody says 110, 115, 120, right? That's what you hear. You're hearing the RMS value. It's always the RMS value unless it's stated otherwise. Assume RMS. Root mean square. Enough information here. Yeah, I want you guys to go ahead and try this and make sure that you